When you find yourself sitting in a neurologist's office, or maybe poring over a new developmental diagnosis for a loved one, you really go in expecting a certain level of, well, mechanical precision.
Right. You expect the medical field to act like structural engineering.
Exactly. Like if you snap your femur, the X-ray illuminates that harsh, jagged white line in the dark. The orthopedic surgeon points right at it, and the path forward is obvious. The bone is broken, we set the bone, and we wait.
Yeah, we crave that visual confirmation. I mean, it provides a definitive boundary between healthy and broken, which is psychologically very grounding.
It really is. But the moment you step out of orthopedics and into the realm of neurodevelopment, things get murky. When we start talking about sensory processing, verbal apraxia, or the broader spectrum of autism, that comforting X-ray machine suddenly seems entirely useless.
Oh, completely. You are thrust into this diagnostic landscape that is just incredibly subjective.
Right. You are handed behavioral checklists instead of imaging scans. And that is exactly why you are going to want to eliminate all distractions and stick around for this deep dive today.
It is a really fascinating topic.
It truly is. We are taking those murky subjective waters and running them through a sort of industrial-grade filtration system. We have a huge stack of technical documentation in front of us outlining a framework called Neuro Recovery Engineering.
And it proposes a paradigm shift that is, honestly, so radical.
It essentially asks this massive question: what if we have been looking at these neurological conditions completely backward?
It demands that we reconsider the very definition of permanent damage. I mean, the core thesis here asks, what if the brain's hardware isn't actually missing or physically destroyed?
Like the actual physical architecture required for speech, socialization, and executive function.
Right. What if that intact, pristine hardware is simply trapped inside a highly protective, inescapable, high-security software loop?
Which, fundamentally changes the mission. The goal of this deep dive is to decode this engineering framework.
We are going to look at how the brain processes incredibly high bandwidth data, like human language.
And why that specific system gets jammed. Plus, how we might actually force a system-level reset. Okay, let's unpack this.
Sounds good. Let's dive right in.
We are going to stop treating the human brain like a mystical, unknowable organ and start treating it like a black box computer system. I mean, we aren't attempting microscopic neurosurgery here.
No, we aren't trying to map the billions of individual synaptic connections.
We are going to optimize the environmental and biological inputs to dramatically alter the behavioral outputs.
And shifting to that systems engineering perspective forces us away from that rather fatalistic view of irreversible structural deficits. We move toward the concept of reversible state issues.
Which is so much more hopeful.
It is. The absolute holy grail of this entire clinical framework is achieving system homeostasis. The engineers refer to this optimal baseline as laminar flow.
I have always loved that term in fluid dynamics.
It's a great visual.
It really is. Laminar flow is when a fluid moves in perfectly parallel layers with absolutely zero disruption or turbulence between them. It looks like glass.
Now apply that physical state to neurobiology. When a brain is operating in laminar flow, the internal background noise is practically non-existent.
So the processing logic is razor sharp.
Exactly. And the biological hardware possesses the necessary voltage headroom to handle massive, complex streams of data without crashing.
Think about navigating a crowded, noisy room while holding a nuanced conversation. A brain in laminar flow handles that data transfer effortlessly.
But to even entertain the idea of guiding a brain back into that smooth laminar state, we have to clear a massive philosophical hurdle first.
We have to prove that the machinery is actually still in there.
Right. If a patient hasn't spoken a word in 5 years, the conventional assumed wisdom is that the speech center has suffered permanent physical atrophy.
Or that it was never fully developed in the first place. So how do we definitively prove the hardware hasn't been wiped out?
Well, the source material addresses that skepticism head-on. They point to one of the most staggering medical anomalies documented in the last 2 decades.
The Zolpidem paradox. I had to read this section of the notes 3 times.
It is wild, isn't it?
It really is. Zolpidem is obviously a profound central nervous system depressant. It is a heavy sedative.
Yeah, it is a powerful GABA agonist. Its entire pharmacological purpose is to suppress global brain activity and induce unconsciousness.
Yet, in the Zolpidem paradox, you have this thoroughly documented cohort of patients existing in minimally conscious or entirely locked-in states.
We are talking about individuals who have suffered catastrophic anoxic brain injuries or massive strokes.
Right, they have been completely nonverbal and practically immobile for years. And then, for various clinical reasons, they are administered this heavy sedative,
And the absolute opposite of sedation happens. They wake up.
which is just mind-blowing. They open their eyes, they recognize their families, they regain motor control, and they start speaking.
From a massive dose of a sleeping pill.
Imagine the emotional whiplash of being a parent or a spouse, sitting by that bed for years. And a central nervous system depressant is what brings your loved one's voice back into the room.
The emotional weight of it is staggering. But the mechanical implications are what we really need to focus on here.
From a purely neurological standpoint, it appears entirely counterintuitive.
It does. But from a systems engineering perspective, it is the ultimate proof of concept. This paradox provides undeniable field-tested evidence of latent hardware.
Because if flooding a patient's brain with a powerful inhibitory drug suddenly restores complex human speech, it proves something massive.
It proves beyond a shadow of a doubt that the language module was never physically eradicated.
Right, because a sedative cannot rapidly construct complex new neural pathways out of thin air. It can't just build a new speech center in 20 minutes.
It simply cannot, which means the hardware was fully intact all along, but it was completely submerged under a 100% white noise floor.
Wow, so the brain in that locked-in state is essentially screaming.
Exactly. It is locked in a state of high alert, high-gain electrical panic. The sedative lowers that baseline noise floor just enough for the pre-existing healthy signal to finally breach the surface.
And push through to the motor cortex. It makes me think of an old analog radio.
Oh, that's a perfect analogy.
Yeah, like if you turn the volume dial all the way up while you were between stations, the static is so violently loud, it shakes the speakers.
And you would naturally assume the radio is broken.
Exactly.
Yeah.
But the broadcast of the music is still happening in the background. The localized static is just drowning it out.
So the zolpidem just turns down the static.
So the wires aren't cut. The alarm bell is just ringing so loudly that the brain can't hear the signal being sent.
That brings us directly to the framework's dual path failure model. The engineers define two distinct ways the neural processing system fails and compromises signal throughput.
Okay, let's break those down.
The first path, which mirrors the loud static of your radio analogy, is high-gain failure. They call this signal saturation.
Let's look under the hood of signal saturation. What is physically generating that localized static inside the black box?
Well, every electrical system has an internal noise floor. In a saturated neural system, this noise floor is driven exponentially higher by specific inflammatory markers.
The text highlights a cytokine called TNF-alpha, right? Labeling it the master game knob.
That's the one. When you combine high levels of TNF-alpha with an excess of excitatory neurotransmitters like glutamate, the noise floor rises incredibly fast.
So rapidly that it violently collides with the hardware's maximum voltage ceiling.
Yes. In circuit design, this is known as hitting the VCC ceiling.
So the system is attempting to process normal daily inputs. But because the baseline voltage is already redlining at the ceiling, every new piece of data pushes the system into an excitotoxic state.
Exactly. The system just can't handle any more load.
What is the observable clinical result of a brain constantly hitting that voltage ceiling?
The clinical manifestation is severe sensory overresponsivity. You witness hypervigilance, extreme tactile and auditory defensiveness.
Like aggressive outbursts and massive behavioral meltdowns.
Right. The individual is not misbehaving. Their biological hardware is quite literally redlining.
Because the brain is interpreting an inherently safe environment as a catastrophic, system-destroying threat, like the hum of a refrigerator or the flicker of a fluorescent bulb.
Or even the texture of a cotton shirt. That represents the high-gain, saturated failure path.
Okay, let's pivot to the second path then.
The second path represents the exact opposite extreme. It is low-gain failure, referred to in the documentation as signal attenuation.
Or more descriptively, a logic brownout.
A brownout, yes. Like a municipal power grid during a massive heat wave.
Right. The grid doesn't experience a total blackout, but the voltage drops so low that the lights flicker and dim. There simply isn't enough raw current to power the heavy machinery.
In neurobiology, this brownout is triggered either by severe lack of mitochondrial ATP production, which is literally a power shortage, or by overactive inhibitory logic.
Where the brain's braking system is just flooring the pedal.
Precisely. The incoming sensory signal is either generated too weakly, or the systemic inhibition is so suffocating that the signal fails to cross the basic detection threshold.
The threshold required for conscious processing. So moving away from the meltdowns of saturation, what does this attenuated brownout state look like in a clinical setting?
It presents as sensory underresponsivity. You observe profound lethargy, significant delays in processing speed, and a very far away or disconnected effect.
The engineering text intriguingly describes this state as autism without overload.
Which is a very profound way to categorize it. The neural system has entered a protective limp mode.
It is intentionally suppressing high-level processing and energy expenditure just to shield the core autonomic operating system from a total collapse.
This is actually where the source material bridges the gap between theoretical engineering and observable biology.
Because they correlate this dual-path model with concrete power spectral density patterns from EEG scans.
The mathematical correlation is striking. When researchers analyze the EEGs of children presenting with severe developmental delays or autism, they rarely see just one isolated type of failure.
Instead, the spectral density graph reveals a highly specific U-shaped curve.
Exactly. Let's break down that U-shape.
You have massive spikes of power on the extreme left, massive spikes on the extreme right, and a severe valley right in the middle.
Let's map those frequencies to the engineering model. On the extreme low-frequency end of the spectrum, the delta and theta waves, these children exhibit excessive, abnormal power.
That massive spike on the left represents the profound brownout, the signal attenuation, the system stuck in limp mode.
Yet, simultaneously on the extreme high-frequency end, the beta and gamma waves, they also exhibit excessive power.
So that spike on the right represents the severe signal saturation, the excitotoxic high-frequency static.
And that valley in the middle of the U-shape, that occurs precisely in the alpha frequency range.
Alpha represents the frequency of relaxed, alert, effortless baseline processing.
It is the electroencephalographic signature of laminar flow. Therefore, the mathematics of the EEG perfectly confirm the dual-path engineering model.
The hardware is completely devoid of laminar flow because it is simultaneously browned out and violently redlining. It is trapped in a state of exhausted panic.
Exhausted panic. That is a harrowing way to exist.
If the hardware is redlining in that manner, we have to look at how it impacts the highest bandwidth application the human brain runs: human speech.
Speech isn't just generating acoustic noise. It requires the instantaneous coordination of vocabulary retrieval, emotional tone mapping, complex muscular timing, and social intent processing.
It is a massive, highly synchronized data transfer.
To comprehend how a saturated system triggers the total collapse of language, we have to introduce a physical phenomenon the engineers call the hysteresis latch.
Hysteresis is a concept we usually encounter in physics, right? Specifically in magnetism or thermodynamics.
That's right. If you apply a strong magnetic field to a piece of iron, the iron becomes magnetized.
But when you remove the external magnetic field, the iron doesn't immediately return to its baseline unmagnetized state. It retains a memory of the polarization.
It stays magnetized. It becomes stuck in that new state long after the initial trigger has vanished.
And the engineers apply this directly to the brain's security apparatus.
Imagine the brain experiences an extreme impulse event, a biological trigger the text refers to as a monster wave of inflammation.
This could be a severe viral infection, a massive environmental toxic exposure, or even a catastrophic physical trauma.
This sudden, violent wave of inflammation impacts the brain's immune sentinels.
The microglia. The documentation refers to them as the system's maintenance drones and the primary security logic.
Under normal circumstances, microglia are peaceful gardeners maintaining the neural environment. But when that monster wave hits, things change rapidly.
They instantly detect the existential threat and flip from their peaceful state into a hyper-aggressive M1 attack state.
They flood the local neural environment with inflammatory cytokines to neutralize the perceived invader. The system operates exactly as designed to survive the acute crisis.
But here is the critical, catastrophic point of failure. After the pathogen is defeated and the trigger is entirely gone, the system latches.
The microglia never flip back. They remain perpetually polarized in the M1 attack state.
The brain fundamentally recalibrates its baseline acceptable noise floor to a permanent high-gain setting.
It treats everyday, benign existence as an ongoing monster wave.
The war is over, but the security forces refuse to stand down. How does that perpetual latch state specifically dismantle the complex data transfer of speech?
The documentation details 3 cascading failure mechanisms here. The first is signal clipping.
Audio engineers deal with this constantly, but how does signal saturation physically distort the audio data of human speech inside the brain?
Picture the digital display on a piece of audio recording software. You have a waveform moving up and down between a defined ceiling and floor.
Okay, I am picturing that.
If you push the microphone's gain way too high and someone suddenly shouts into it, the incoming sound wave requires more physical space than the digital ceiling allows.
So the beautiful rolling peaks and valleys of the sine wave literally hit the digital ceiling and get violently chopped off.
That is signal clipping. It flattens the complex rolling wave into a harsh, blocky square wave.
To the human ear, a square wave sounds like a blown-out speaker at a heavy metal concert. It's an agonizing, crunchy, harmonic distortion.
Apply the physics of that audio clipping directly to the auditory processing center of a latched brain.
The internal inflammatory noise floor is already hovering millimeters below the absolute VCC voltage ceiling.
There is zero electrical headroom available, so when a complex packet of human language data arrives, it instantly and violently collides with that low-voltage ceiling.
And this packet is carrying vital subtleties like emotional nuance, gentle inflection, and social intent. The speech signal is brutally clipped.
The neural hardware physically flattens the incoming language data into a distorted square wave.
That reframes so many behavioral observations. To a child trapped in this latched state, a parent speaking to them in a soothing, comforting voice doesn't register as soothing at all.
The data is clipping. It literally sounds like physical pain or a wall of overwhelming static.
It is no wonder a child might cover their ears or avert their eyes. The sheer volume of the data is physically hurting their overloaded processing centers.
The hardware is simply incapable of accommodating the size of the data packet at its current latched gain setting without severe exciter-toxic saturation.
Wow, that addresses the incoming signal. But what about the outgoing signal?
The second mechanism of failure is what the engineers call the rat's nest and hyperconnectivity.
And I have to push back hard on this concept based on modern neurodiscourse. For the last 2 decades, the pop science consensus around neuroplasticity has relentlessly pushed the idea that more synaptic connections equate to a faster, more robust brain.
That is a very common perspective, yes.
We are constantly told to build more neural pathways. How can an excess of wiring be the cause of failure?
It is a pervasive oversimplification of neurobiology. In high-level systems engineering, an abundance of wiring is a catastrophic liability if that wiring is disorganized, redundant, and completely uninsulated.
Okay, that makes sense.
When those microglia are latched in their M1 attack state, they completely abandon their primary vital peacetime function.
Which is synaptic pruning.
Yes, synaptic pruning is the continuous, meticulous optimization of the neural network.
In a healthy laminar system, microglia act as ruthless efficiency experts,
constantly trimming away weak, redundant, or obsolete synaptic connections, ensuring that the primary data highways remain fast and isolated.
But in the M1 state, the pruning shears are dropped in favor of inflammatory weapons. The background garbage collection algorithms completely halt,
leaving the neural wiring to grow wildly unchecked, creating chaotic, localized hyperconnectivity.
The text uses the term the rat's nest, which is a perfect visual.
And the physical crisis of a rat's nest lies in the physics of electromagnetism. Without meticulous spacing and robust insulation, specifically the protective myelin sheath wrapped around healthy neurons, you suffer from severe inductive coupling.
Let's visualize inductive coupling. If you run a bundle of cheap, uninsulated copper wires next to each other and you send a massive jolt of high-voltage current down one specific wire,
the invisible electromagnetic field generated by that current will cause the signal to jump, or arc, into the adjacent wires.
the signal bleeds across the physical boundaries.
Inside the brain, imagine a child attempting to send a highly precise, high-definition motor command to their vocal cords to articulate a specific word.
Because the pathway traverses a highly conductive rat's nest, that pristine signal violently bleeds into neighboring auditory, emotional, or gross motor pathways.
The outgoing signal completely loses its target destination. It introduces massive logic jitter into the system.
The precision required for verbal output is obliterated by crosstalk.
This provides a clear mechanical root cause for conditions like verbal apraxia. The child's internal thought process knows exactly what it wishes to communicate.
But the final motor execution is garbled because the signal is jittering wildly across uninsulated pathway.
Or consider echolalia, where the vocal output is highly repetitive and contextually misaligned.
It is not a willful behavioral refusal to engage in novel speech. It is a symptom of a data bus suffering from massive, uncontrollable signal bleed.
That analogy of the signal jumping the tracks is incredibly helpful.
So we have Incoming speech clipping into painful static and outgoing speech jittering across the rat's nest. The third mechanism involves power distribution, mitochondrial brownouts.
We touched on this briefly, but we really need to dive deeper into the sheer energy economics of language.
Human speech and the continuous social synchronization required to interpret and respond to another human being is arguably the most energy-intensive, high-bandwidth application the brain runs.
It demands massive, continuous power draw, and the local power generators within the cellular structure are the mitochondria.
The engineering framework designates them as voltage regulator modules, or VRMs.
If the entire neural system is locked in a state of chronic latched inflammation, these VRMs are constantly running at maximum capacity just to manage the thermal stress.
Eventually, they become completely exhausted.
They enter a localized limp mode, creating a severe power brownout.
Think about a smartphone when the battery drops below 5%. The operating system doesn't just let the phone die abruptly.
It initiates emergency protocols.
It dims the screen, turns off background syncing, disables the GPS, and aggressively shuts down any high-energy, non-essential applications to preserve the absolute minimum power required.
The biological operating system operates on the exact same preservation logic, to protect the core kernel.
The autonomic centers in the brainstem controlling vital functions like respiration, heart rate, and basic homeostasis.
The system ruthlessly prioritizes its dwindling energy reserves. It forcefully throttles or completely shuts down massive high-energy applications that are deemed non-essential for immediate physical survival.
Complex, nuanced speech and the processing of subtle social cues are always the first to be taken offline.
So, synthesizing those three mechanisms, the speech application is either actively crashing due to a severe lack of mitochondrial power,
Or the outgoing data is being garbled by uninsulated crosstalk in the rat's nest.
or the incoming data is painfully clipping against a saturated voltage ceiling.
If I am a parent or a physician tasked with treating this, how do I begin to diagnose a system this chaotic? How do we pinpoint where the failure is originating within the black box?
This requires the clinician to temporarily abandon traditional medical diagnostics and adopt the mindset of a network IT technician.
The critical first step is differentiating between an infrastructure failure and an operational failure.
To make this distinction, the framework relies on two primary metrics: the MRS, or Logistics Stability Index, and DTCs, which stand for Diagnostic Trouble Codes.
Let's clearly define those variables. What physical system serves as the logistics hub in this neuroengineering model?
The logistics hub is the human gastrointestinal tract and the vast, complex ecosystem of the microbiome. It is the absolute foundation of the entire system.
It acts simultaneously as the power supply, synthesizing critical neurotransmitters, and the primary supply chain.
Processing and distributing the raw biological materials required for neural repair. The MRS is a clinical readiness score scaled from 1 to 10 that evaluates the absolute stability and integrity of this biological hub.
And the DTCs, what exactly are they?
Diagnostic trouble codes are the observable real-time behavioral spikes: severe meltdowns, aggressive stimming, violent selects, sudden regression.
These are the physical error codes the central processor throws when it is actively failing to process its environment.
Let's run a theoretical diagnostic to see how this differentiation works. Scenario A.
Okay, lay it on me.
A patient presents with a significantly low MRS score, let's say hovering around a 4 or 5. Their digestion is terrible.
And simultaneously, they are exhibiting massive daily behavioral spikes, throwing constant DTCs. What is the engineering interpretation of that specific data set?
A low MRS score instantly flags the situation as a catastrophic infrastructure failure. The logistics hub is in a state of active, hostile dysbiosis.
There is a physical breach in the supply chain architecture, which the text refers to as a logistics leak.
The gut is highly permeable, and it is actively injecting what the engineers call dirty current directly into the systemic bloodstream.
And up into the neural communication bus. The source material is highly specific about the nature of this dirty current. It highlights lipopolysaccharides, or LPS.
Alongside neurotoxic metabolites like propionic acid, lipopolysaccharides are endotoxins found in the outer membrane of certain pathogenic bacteria residing in the gut.
In a healthy system, the tight junctions of the intestinal wall keep these endotoxins contained.
But in a compromised, leaky hub, the LPS molecules breach the barrier, enter the bloodstream, and eventually cross the blood-brain barrier.
When this highly inflammatory dirty current washes over the microglia, the system is stripped of all available voltage headroom.
The baseline noise floor is permanently and violently pegged to the VCC ceiling.
This establishes a crucial, non-negotiable rule for anyone listening. You do not attempt to rewrite the brain's software or introduce complex behavioral therapies when the biological power supply is actively pumping highly toxic inflammatory sludge directly onto the motherboard.
You don't try to install a new high-end graphics card in a computer that is actively submerged in water.
Exactly. So what is the immediate clinical action in scenario A?
The clinical action must be aggressively, exclusively focused on the infrastructure. The engineering manual states you must first seal the gate and cool the radiator.
Sealing the gate requires absolute draconian dietary exclusion, methodically removing the specific energetic inputs that are fueling the proliferation of the pathogenic LPS-producing bacteria.
And cooling the radiator involves deploying systemic baseline antioxidants to absorb the immediate thermal oxidative stress.
You must force the foundation into stability before you even consider addressing the central processor.
Let's contrast that with scenario B. We run the diagnostic and the gut appears incredibly stable. The MRS score is a solid, consistent 9 or 10. Digestion is visually perfect.
Yet, the patient is still throwing acute, violent TTCs. They're still experiencing sensory meltdowns. If the power supply is completely clean, why is the machine still crashing?
Scenario B defines an operational failure. The infrastructure is solid, the gate is sealed, but the central processor is deeply overwhelmed by internal logic errors.
The engineers interpret these acute meltdowns as a purge surge.
Or the result of an internal impulse event, perhaps a latent viral flare. The processor is experiencing severe signal clipping despite receiving a perfectly clean power feed from the gut.
It's no longer a dirty current problem. It's strictly an internal volume problem.
Precisely. It is purely a failure of gain management. The internal amplifier of the latched microglia is simply dialed far too high.
The clinical action required here is to physically pad the signal.
You have to introduce components that artificially prevent the voltage from clipping against the ceiling, creating enough temporary stability to apply a manual system override.
An override that forces the microglia to switch their logic state. That provides the perfect transition into the actual mechanical intervention.
Let's assume the logistics hub is fully stabilized. We know the gut is sealed, the duty current is halted.
How do we mechanically manage that internal gain to bring the speech application back online? How do we construct that signal padding?
This brings us to the core of the framework, the Phase 2 shield deployment.
Here's where it gets really interesting. The shield deployment is the process of installing a temporary, highly targeted biochemical protection circuit around the central processor.
The goal is to manually expand the available voltage headroom and physically force the localized noise floor to drop.
This is not just high-level theory. The documentation provides an exacting step-by-step engineering checklist.
But before we build the shield, there are severe prerequisites. You cannot simply start throwing supplements at a saturated system.
You must clear the safety gate.
The framework mandates that the patient must maintain that high MRS score of 9 or 10 for at least 7 consecutive days.
Furthermore, they must have completed a minimum of 21 days on an absolutely ruthless, 100% strict dietary lockdown.
The standard protocol requires the total elimination of gluten, casein, soy, and high fructose corn syrup.
Additionally, the immediate physical environment must be heavily neutralized, particularly removing volatile organic compounds, or VOCs, like airborne ammonia or harsh metallic odors.
It is incredibly strict.
Let me play devil's advocate for a moment regarding that 21-day strict diet. Is the system truly that fragile? If a child has been perfectly compliant for 20 days and they accidentally consume a single cracker containing casein, does that really compromise the entire engineering framework?
It absolutely does because of the threshold effect of biological EMI, electromagnetic interference.
So any small slip-up is catastrophic.
If you fail to respect the prerequisite safety gate, any sophisticated biochemical shield you attempt to build will be instantly bypassed by a fresh surge of dirty current.
A single systemic leak of casein generates a sufficient wave of inflammatory LPS to instantly peg the noise floor back to the ceiling.
Building a shield on a compromised foundation is akin to frantically bailing water out of a sinking boat while aggressively refusing to plug the massive hole in the hull.
The foundation must be immaculate. Assuming the gate is perfectly sealed, the protocol dictates introducing the shield components sequentially, one at a time.
Meticulously observing the system for the slightest measurable nudge in baseline stability. The primary component is the NAC heatsink. NAC stands for N-acetylcysteine.
The The manual refers to it as the coolant. What is the mechanism of action here?
NAC acts as a powerful precursor to glutathione, which functions as the human body's master intracellular antioxidant.
If we return to our engineering terminology, it acts as a literal heat sink for the processor.
When the brain is locked in that aggressive M1 attack state, the sheer volume of inflammatory activity generates massive amounts of cellular oxidative stress.
The engineers view this as destructive thermal noise.
The NAC coolant aggressively absorbs that biochemical heat, preventing the delicate neural architecture from melting down. It establishes the primary damping ratio for the entire circuit.
It essentially stops the hardware from vibrating itself to pieces. Following the coolant, the next critical component is the inositol signal pad.
The text refers to this as the current limiter.
I really want to understand how inositol physically pads a neurological signal.
This component is the absolute core of the gain management strategy. Inositol is a naturally occurring sugar alcohol that is heavily involved in regulating cellular signaling.
Particularly concerning calcium release and neurotransmitter action.
In a highly saturated latched system, the noise floor is constantly colliding with the voltage ceiling. Every minor sensory input causes violent excitotoxic clipping.
The introduction of inositol mathematically modulates that signaling threshold.
It acts as a biochemical buffer, a literal dampening pad inserted between the rising noise floor and the rigid VC ceiling.
Returning to our audio engineering analogy, by installing this current limiter, we turn down the internal amplifier.
The complex audio wave of incoming speech stops violently smashing into the ceiling, and it stops flattening into that agonizingly distorted square wave.
Exactly. By artificially expanding the voltage headroom with inositol, the incredible high-definition nuance of human language finally has adequate physical space to exist.
The subtle emotional tone, the intended meaning, the complex vocabulary, it all fits inside the hardware without triggering an excitotoxic crash. The painful distortion ceases.
That mechanism alone is profound. And finally, the shield requires a grounding mechanism, the glycine ground.
Every high-voltage electrical circuit requires a safe, robust path to ground to prevent catastrophic failure.
Glycine, acting as an inhibitory neurotransmitter, provides that necessary electrical path,
allowing all the excess, highly toxic, excitatory voltage, specifically the surging glutamate static, to safely and continuously dissipate out of the primary neural bus.
So the completed shield consists of the coolant absorbing the thermal stress, the pad artificially expanding the voltage headroom, and the ground safely draining the excess static.
Once the shield is fully deployed, the system enters the telemetry window.
The critical 12 to 48-hour observation period. This is where the clinician watches intently for a successful system baseline transition.
What are the specific visual indicators of success?
The indicators are striking. You are looking for the clinical return of hardware headroom, which immediately manifests as a sharp, sudden cessation of those behavioral DTCs.
The meltdowns just evaporate, but most importantly, you're looking for the spontaneous occurrence of what the framework calls the zolpidem delta.
The zolpidem delta, circling all the way back to the paradox we discussed at the beginning. But in this instance, we aren't administering a massive dose of a sedative.
We are simply waiting for that exact same emergence of the latent signal.
Yes. Because you have successfully manually lowered the noise floor using the biochemical shields, you often witness something seemingly miraculous.
The sudden emergence of sustained eye contact, a drastically calmer, engaged disposition, or the spontaneous, unprompted articulation of novel words.
The underlying linguistic and social signal was always present. You simply engineered the localized environment to be quiet enough for that signal to finally be detected.
It is a stunning concept, but we have to remain grounded in reality. We are manipulating incredibly complex biological systems.
What occurs when a clinician executes this exact checklist, deploys the shields perfectly, waits the 48 hours, and absolutely nothing happens?
Zero delta. The system remains highly volatile. Do they abandon the framework?
Absolutely not. The engineering manual contains exhaustive protocols for troubleshooting a failed shield deployment.
When results fail to manifest, you don't discard the theory. You systematically hunt down the unknown variables corrupting the circuit.
The text provides specific diagnostic steps for a zero-result scenario. The first step, predictably, is investigating a logistics leak.
This remains the single most common point of catastrophic failure. If the shields produce zero clinical results, it is almost a statistical certainty that the logistics gate was not sealed.
It has to hit that 100% threshold. The engineer must initiate a rigorous root cause analysis and comprehensively re-audit every single aspect of the supply chain.
This reiterates your point about the threshold of biological EMI. The manual stresses that a single microscopic leak of a restricted protein creates enough dirty LPS current to render the entire protection circuit useless.
It really highlights the extreme sensitivity of a latched neural network. The clinician has to enforce a stricter lockdown.
Identify the hidden exposure and ensure the foundation is completely impermeable before attempting to redeploy the shields.
Let's escalate the scenario. What if the clinician audits the supply chain and the diet is truly flawlessly perfect, but the patient still exhibits zero results?
That leads us to step 2, triad variants. The documentation introduces the concept of the brain's CPU triad. Break that down for us.
The neurovascular unit, which the engineers refer to as the CPU triad, is fundamentally composed of 3 interconnected nodes: the microglia, the astrocytes, and the neurons.
The framework acknowledges that every individual patient represents a unique hardware revision.
This means the historical impact of the hysteresis latch may have degraded one specific node significantly more severely than the others.
A generic shield won't work. You must customize the biochemical deployment based on the specific node sensitivity.
So if the diagnostic suggests the failure is heavily localized in the microglia node, meaning the security logic is the most stubborn, deeply latched component, how do you adjust the shield?
You must dramatically increase the system override capability. This involves deploying high targeted doses of rutin,
Which is a specific bioflavonoid that acts as a direct potent inhibitor of TNF-alpha.
You run the rutin alongside the NAC coolant to forcefully and aggressively compel the microglia out of their entrenched M1 state.
What if the variance is astrocyte heavy? The astrocytes act as the critical vacuum cleaners of the neural environment, correct?
They are responsible for meticulously clearing the highly toxic glutamate static off the neural bus.
If the astrocytes are physically failing or clogged, the text suggests a fascinating mechanical intervention.
Utilizing high silica water, such as Fiji water, to physically bind to and clear the intracellular grit that is clogging their cellular vacuum mechanisms.
You have to clean the vacuum before the shields can effectively lower the noise floor. And if the variance is neuron heavy,
If the actual physical cables transmitting the data are deeply degraded, then the engineering focus must immediately pivot to refurbishing the physical chassis.
the clinician needs to deploy high therapeutic doses of specific lipids, primarily choline and DHA.
To actively repair and rebuild the degraded myelin insulation, you have to physically stop the inductive coupling and signal bleed before the logic jitter will cease.
The required level of customization is intense. This isn't a scenario where you simply prescribe a single, one-size-fits-all pill and hope for the best.
It is a highly dynamic, continuous tuning process. But the text mentions one final major roadblock when troubleshooting a failed shield. They call them logic slugs.
Nutritional deficiencies acting as catastrophic logic slugs within the system architecture.
I want to use a software analogy to visualize this. Imagine you are attempting to install a massive, critically important software update on your laptop.
You initiate the install, but the system runs a background check and realizes the hard drive is completely out of available storage space.
The update cannot download the necessary files. The entire operating system just hangs. It freezes in an incomplete state.
That is precisely how a logic slug operates within human neurobiology. The overarching background operating system of the human body is the methylation cycle.
It is an incredibly complex biochemical engine responsible for passing logic bits around, managing intricate DNA expression, and running continuous background garbage collection.
But to run that underlying operating system smoothly, the body demands an uninterrupted supply of highly specific raw biological materials.
Without those materials, the engine seizes. If the patient's system is chronically deficient in critical components like B12, folinic acid, magnesium, or zinc, the core methylation kernel physically stalls.
A clinician can deploy all the meticulously balanced inositol and NIC they want. But if the background OS is frozen due to a severe lack of basic nutritional components, the protection shields literally cannot be written to disk.
The biochemical instructions cannot be compiled. The system hangs indefinitely.
Meaning the clinician must run comprehensive nutrient panels and patch the kernel OS with those specific elements before the system will even accept the shield deployment.
Okay, let's assume the clinician has successfully navigated all the troubleshooting protocols.
The logistics hub is impeccably sealed. The CPU triad is perfectly balanced. The logic slugs have been identified and cleared.
The shields are fully operational, and the baseline noise floor has finally plummeted. The system is incredibly quiet. Are we finished? Is the patient cured?
We are absolutely not finished. The system is beautifully quiet and the patient's behavior is drastically calmer, but the underlying hardware, specifically that massive chaotic rat's nest of unpruned, uninsulated wiring, is still physically configured incorrectly.
The patient is stable, but they are entirely dependent on the artificial presence of the shields to maintain that stability.
We have merely managed the symptoms. We haven't eliminated the root cause. It is time to initiate the hard reset.
The hard reset, the framework calls this the active flush. Just the name sounds incredibly intense.
It represents the most critical, high-stakes transition in the entire clinical framework. We are moving away from static maintenance, where we are merely padding the signal and keeping the system quiet.
And transitioning into dynamic structural reset.
We're no longer simply hiding from the noise. We are going deep into the infrastructure to physically locate and eradicate the biological root cause of the hysteresis latch.
The documentation refers to this physical eradication as industrial debridement. What exactly are we debriding inside the logistics hub?
We are systematically dismantling the hardened, calcified biofilm scaling and the deeply embedded pathogen nodes residing within the gastrointestinal tract.
These biofilms are incredibly resilient, architecturally complex fortresses constructed by malicious bacteria to protect themselves from the immune system.
And they are the ultimate perpetual source of that standing wave of biological EMI.
They are the factories continuously producing the dirty current that keeps the brain's security alarm blaring year after year.
Exactly.
Yeah.
Utilizing a combination of highly specific biofilm disruptors and targeted, robust antimicrobials, the engineer executes what is essentially a biological high-pressure line cleaning of the entire logistics hub.
There is an incredibly illuminating sidebar in the documentation regarding a phenomenon known as the colonoscopy effect.
Oh, this part is fascinating.
It provides a stunning real-world proof of concept for what the active flush is attempting to achieve. Let's explore that.
It is one of the most fascinating and frustratingly ignored clinical phenomena in modern gastroenterology and neurology.
For decades, thousands of parents and attending physicians have independently documented a bizarre occurrence. Autistic children often experience a rapid, dramatic, and profound transient remission of nearly all their core neurological symptoms, specifically during the grueling bowel prep phase of a routine colonoscopy.
For a window of 24 to 48 hours, these children suddenly make piercing eye contact. Their crippling sensory overload entirely vanishes.
And nonverbal children might suddenly speak in complete, contextually appropriate sentences.
And the conventional medical establishment frequently dismisses it. They call it a mysterious coincidence, or they attempt to attribute it vaguely to the anesthesia.
Completely ignoring the fact that the remission often begins during the prep phase, long before the anesthesia is administered.
To a neuro recovery systems engineer, it isn't a mystery at all. It is glaringly mechanically obvious.
The bowel prep induces a massive involuntary global system purge. By aggressively and violently flushing the entire GI tract with osmotic laxatives, you cause a massive, immediate, albeit temporary, reduction in the localized biological EMI.
The production and absorption of inflammatory LPS drop practically to zero.
And because that massive wave of dirty current abruptly halts, the noise floor in the brain plummets, the hysteresis latch temporarily breaks, and that zolpidem logic we discussed earlier engages.
The true, intact, uncorrupted signal emerges from the noise. It is the ultimate, undeniable field test proving that the neural hardware functions flawlessly when the gut isn't actively poisoning the primary data bus.
It perfectly validates the entire model. The active flush protocol is attempting to achieve that exact same profound system purge, but permanently.
By methodically dismantling the biofilm fortresses rather than just temporarily washing over them.
So, as the active flush successfully debrides the biofilms and permanently drops this massive wave of biological noise, what physically happens up in the brain? This seems to be the critical pivot point of the entire framework.
With the persistent, agonizing noise finally eradicated, the central security alarm of the neural network stops ringing.
The microglia, which have been violently stuck in the M1 attack state for potentially years, finally receive a sustained, clear biological signal that the systemic environment is genuinely safe. And they flip.
They break the hysteresis latch.
They break the latch. They transition out of the highly inflammatory M1 attack logic and revert back to their default, peaceful baseline state, the M2 repair logic.
The drums finally put down their weapons. Once they transition into repair mode, what is their immediate priority? What do they actually do to the hardware?
They immediately pick up their pruning shears. In the M2 state, the microglia resume the critical process of synaptic pruning.
This is the massive background kernel optimization
Mhm.
that the brain has been desperately scarved of.
The microglia look at that chaotic, overgrown rat's nest of wiring, which they can finally map clearly because the blinding static is gone.
And they begin the meticulous systemic work of trimming away the redundant, uninsulated, and highly leaky synaptic connections.
They are physically cutting away the errant pathways that were causing the massive signal bleed and the crippling logic jitter. They are structurally repairing the hardware.
Precisely. And this is the moment where we can connect this vast, complex engineering model all the way back to our opening question regarding the seemingly miraculous recovery of language.
Why does targeted hardware restoration inevitably lead to spontaneous language recovery? Because once the massive rat's nest is pruned down to its most efficient pathways.
And those remaining critical data paths are heavily re-insulated with the choline and DHA we introduced earlier.
The system successfully achieves laminar flow.
Yes, the incredibly dense, high-bandwidth data packets of human speech can finally travel from the thought origination center in the cortex, down through the motor pathways, and out to the vocal output modules.
Without violently hitting a saturated voltage ceiling, without arcing into a neighboring emotional pathway, and without being abruptly shut down by a desperate mitochondrial brownout.
So the most profound paradigm-shifting takeaway from this entire text is that in many of these cases, you do not necessarily need to teach the child how to speak from scratch, as if the fundamental knowledge or capability was entirely absent.
The cognitive signal was always intact. The intent to communicate was desperately there.
Once the chaotic wiring is pruned and heavily insulated, the pristine, intact signal is finally permitted to traverse a streamlined, highly optimized data bus.
The complex language simply emerges naturally and spontaneously from the newly quieted environment.
It represents a complete fundamental inversion of traditional therapeutic approaches.
Instead of relentlessly attempting to force complex behavioral data into a highly saturated, painfully clipping system, the engineer focuses entirely on optimizing the physical hardware.
Trusting that once the noise floor drops, the system possesses the inherent capability to seamlessly process its own data. What an absolutely staggering journey.
It really is a lot to process.
Let's try to summarize the immense scope of what we have covered today, because the sheer volume of technical ground is massive.
We began by challenging the utility of the broken X-ray machine metaphor.
We stopped viewing complex developmental disorders as permanent, physically broken hardware and learned to treat them as saturated, stubbornly latched software.
We established the undeniable proof that the underlying hardware remains structurally intact by analyzing the profound implications of the Zolpidem paradox.
We decoded how the brain gets trapped in a hysteresis latch, perpetually redlining in an M1 attack state.
Which physically clips the incoming speech signal into a painful square wave and simultaneously generates a hyperconnected rat's nest of wiring that utterly destroys the precision of verbal output.
We differentiated between operational and infrastructure failures, establishing the absolute, non-negotiable necessity of perfectly sealing the logistics hub, the gut, to halt the systemic flow of dirty, LPS-driven current.
We walked through the meticulous deployment of the Phase 2 shields, cooling the thermal stress with NSC, padding the gain with inositol, and grounding the excess excitatory static with glycine.
We troubleshot the logic slugs. And finally, we explored the intense execution of the active flush, destroying the deeply embedded biofilms, breaking the hysteresis lash, and finally providing the microglia with the pristine cleanroom environment they required to prune their own wires and restore perfect laminar flow.
It is, without a doubt, one of the most comprehensive and awe-inspiring clinical frameworks I have ever read.
It is a monumental achievement in cross-disciplinary science. But if we take a moment to step back and connect this hyper-specific framework to the broader picture of human biology, it raises a profoundly provocative question.
This specific engineering manual utilizes autism, severe sensory processing disorders, and developmental delays as its primary case studies for demonstrating the hysteresis latch.
But the underlying laws of biological engineering are universal. Take that a step further. What are the broader implications?
Consider the fundamental premise, the catastrophic failure of dynamic homeostasis. This exact same hysteresis latch, where the CPU triad gets violently stuck in a high-gain, self-destructive, inflammatory loop.
If that mechanical failure is the common denominator, how far does this paradigm extend? Think about the devastating progression of Alzheimer's disease.
Is it possible that Alzheimer's is not an unstoppable decay? but rather a massive rat's nest composed of accumulated amyloid debris creating severe bus impedance driven by a latched immune response.
Think about multiple sclerosis. Is it simply a scenario where the brain's latched security logic is misfiring and actively, continuously attacking the dielectric myelin insulation?
Consider Parkinson's. Is it primarily a localized severe mitochondrial brownout where the specific power regulators in the motor cortex have completely failed due to chronic thermal stress?
That is a staggering line of thought. If major, seemingly disparate conditions like Alzheimer's, Parkinson's, and MS all share this exact same foundational mechanical failure of dynamic homeostasis,
How many other devastating, traditionally permanent human conditions are actually just latch systems waiting for the exact right sequence of engineered reset commands?
are we, as a medical society, vastly underestimating the human hardware's inherent miraculous ability to rapidly heal itself once the biological noise floor is finally forced to drop?
That is a concept that demands serious, sustained contemplation.
The clinical implications are truly boundless. When you stop obsessively treating the diagnostic label and start meticulously engineering the underlying human hardware platform, the potential ceiling for profound recovery shifts dramatically.
It fundamentally rewrites what is possible.
I want to sincerely thank you for tuning in and joining us on this incredibly dense deep dive today.
The source materials we explored offered a profoundly challenging and frankly deeply hopeful new lens on the mechanics of human recovery.
It challenges all of us to look far beyond the superficial surface level of behavioral symptoms. I strongly encourage you to look at your own system noise a little differently today.
Are you constantly redlining? Is your internal gain set too high?
Take some time to think about it. Because as we have so clearly learned today, the underlying hardware usually isn't broken. Sometimes the connections are just a little uninsulated. We will catch you on the next deep dive.